Okay, we'll go ahead and get started now. Today will be our fifth day of lecture, and we'll be covering trees advanced lecture. So today we're going to be covering first a different way to do DFS compared to the recursive way we taught yesterday. Then we'll be going through a new technique called tree rerouting, and finally we'll be going over centroid decomposition. So first we'll be covering iterative DFS. So you might be wondering like what's wrong with the DFS we learned yesterday with the normal recursive DFS? Well, in Python and in many other languages, recursive DFS is like extremely slow. So for example, this is just a sample DFS problem we submitted to, and it got time limit exceeded, and a bunch of tests were really close to the time limit. Whereas if we implement this new kind of DFS, our max time is just 0.47 seconds, and we have speedups of like 3 times, like 4 times for certain test cases. So, like, what is this like magical DFS algorithm, and how does it speed things up so much? So here's a side-by-side kind of comparison of the two codes. I'll do a live coding of the iterative DFS, so don't worry too much about understanding that right now. But in our recursive DFS, if you recall, we just have like a function, and for every child of the current node, we call the function on that again, and we do some sort of computation. Whereas instead, if we do iterative DFS, instead of directly doing function calls, which is extremely expensive in Python and very time consuming, we can kind of simulate our own function calls. Um, Using what's called a stack. So let's kind of just go through an example of iterative DFS instead of looking at the code. So the example problem we'll solve is to be solving for all subtree sizes using DFS. So remember we did that last time using recursive DFS. So what we'll do is we have a stack here. This is just a list, except we'll only be removing from kind of the end of the list. So the list will like grow upwards and we'll only remove from the top. And in the stack, we'll be storing the node we're currently at, the parent of the node, and kind of like a status. So like it'll either be 0 or 1, where a 0 means like we haven't processed it yet, and a 1 means we've already processed it. And we also initialize all of our subtree sizes to 1 since like each node contributes 1 to its subtree size. So we initialize our stack with like 1, which doesn't have a parent since it's the root, and a 0 status because we haven't processed it yet. And this is kind of like our initial call to our DFS function in the recursive method. So when we do this, we each time we iterate through a stack, or each time we do our DFS thing, we take the top element from the stack. So in this case, it's our element 1 with status 0. And we say, okay, it hasn't been processed, so let's begin processing it and mark it as processed. So we turn this into a 1. That means we've begun processing it. Then we go to its children, and we also add them to the stack because we want to kind of queue them up for processing later. So we'll add them to the stack, both of them with parent 1 and status 0 because we haven't processed them yet. Then we've kind of finishing processing 1 initially by kind of queuing up its children for work. So we'll go back through and take the top element from the stack again. So in this case, it's node 3, and we haven't done any processing on it, so we'll mark it as like we start processing. But it has no children to queue, so it just kind of like finishes. Then we look at the top element of the stack again. So now it's 3 with it's node 3 with status 1. And what a status 1 means is we've already like finished processing it, and as a consequence, like all of its children have finished processing as well. And 3 has no children, so this is kind of redundant. But what we can do is we can kind of just terminate 3 since we've already finished processing it. So we remove it from the stack and we kind of like ignore it for now. So next we go again, look at the top of our stack. It's now node 2 with status 0, so we begin processing it, and then we add its children to the stack. Then we go through again, take the top element, it's a 5, we mark it as processed, it has no children, so we stop. Same thing for 4. We mark it as processed. It has no children, so we terminate. But now comes the interesting part. We now take the top element of the stack, which is 2, with status 1. The status 1 means we've already like initiated the children processing and the children have already finished. So what this means is that the subtree sizes of its children have already been updated. So what we can do is we can now update node 2 with the subtree sizes of our children. So we can just add the subtree sizes of nodes 4 and 5, which are its children, to the subtree size of node 2, giving it a node 3. So after we finish this calculation, we've kind of like done everything we need to for node 2. So we can remove it from the stack as well. And now we're left back at node 1. So with node 1, we look, the status is 1. So that means we've already like initiated processing with it. And its 2 children have already finished like computing their subtree sizes as well. So we can just calculate node 1 subtree sizes by adding up the subtree sizes of its children as follows. And after we do this, we're also done with processing node 1, so we can remove it from the stack as well. And now that the stack's empty, we've terminated our DFS and we've kind of simulated our entire DFS call. So at the end, similar to like recursive DFS, we were left with our answer array storing the subtree sizes of every node. And I guess just as a recap, the main kind of principle of this is that you enqueue your children into your stack. And then once your children all finish processing, you go back to your node and then you calculate something based off your children, which is in this case your subtree size. So this avoids the expensive function call overhead while still kind of like allowing you to retrieve results from your children. So are there any questions on either this example or iterative DFS in general before I dive into live coding? Okay, so we'll be solving this problem, which is just you want to calculate the subtree sizes minus 1 for every node. And we're given kind of like the parents of a bunch of like employees. So to do this, all I have to do is kind of implement our subtree size calculation. So yeah, so our input is given in the forms of like employee 2 through n, their parents. So we'll start with our n is the number of employees. Then we'll get like the kind of the next line. So and we'll construct our adjacency list using this. So because adjacency lists are in general a very useful way to represent trees and graphs in general. So we'll go through a line. So the parent of I is line I minus 1. So we'll just kind of add this edge into our adjacency list. So now that we have our adjacency built out, we've kind of constructed our tree. We can begin to run our iterative DFS algorithm. So we'll construct our answer array, which is just our size. We'll initialize everything to 1. And then we'll make our function called like DFS subtree size. And then we'll start at some root. So remember we need our stack. So our stack will initialize to like a list with only one element in it, which is like the root with no parents and status 0. So as a reminder, we have node parent status. Then while our stack is not empty, which means like we still have more like work to do. So while stack, this just means like while the stack is not empty, we'll like kind of pop out the node, the parent, and the status of like the work that I have to do. So this takes kind of like the top of our stack and just like removes it. So there's 2 cases here depending on what the status is. So status is 0, start processing it. So we'll first add in, this kind of marks it as processed. So it like replaces the 0 in our stack with a 1 for status. And then we'll go through all of its children. So for all children in the adjacency list, C can't be the parent. So now C has to be one of the children. So we'll kind of append the child also for work. And the parent of our child is our node, and we'll have status 0 since we haven't started processing it yet. Okay, so this kind of finishes our like beginning to process this node, since we basically ask it like, okay, let's first compute all of our children. So if the status is 1, that means we've already queued the children and they've finished. So this means we can begin like actually computing our values based off our children's values, since those are finished processing. So for example, we can do like size. Oh, so we'll iterate through our children again. And we'll do like size of node. We'll add the size of the child. So this kind of, since we've already computed the subtree sizes of all of our children, we'll be able to kind of add those to our current subtree to build up the full subtree size. So after we've done this, we don't have to do anything else to our stack since we've already popped out this element. And we'll just keep going through this until we've exhausted our stack, meaning we've gone through our entire tree. So after this, we'll just run our DFS subtree size starting at root 0, and then we'll print out our sizes. What this does is it like prints them out with a space in between. So let's try running this code. Sorry. This should be I-1 because there's only n-1 elements. So let's run this. So we get subtree sizes of 5 for the root, which makes sense because we have 5 elements, and then 2, 2, 1. If we look here, we have 4, 1, 1, 0, and that's because we want those subtree sizes -1. So to just transform this into our answer, we can just subtract 1 from everything. So we can do this, run it again, and we get 4, 1, 1, 0. So let's try submitting this and see if it's fast enough. So I tried this before with normal DFS and it times out. That's the screenshot you saw earlier. It'll time out. But if we use iterative DFS here, we can wait for the result. And yeah, we got accepted in 450 milliseconds, which is under half the time limit. So comfortably passes just if we change our recursive DFS into this kind of iterative approach. So are there any questions about like either like status or like kind of the casework we do here or anything about this code?
Why would C ever be the parent? Is that in the case of like duplicates?
Because let's say let me go back here. So for example, let's say we're at 2 right now. And its adjacency list includes 1, 4, and 5. So if we iterate just through the adjacency list, we'll end up with all of its children plus its parent. But we want to kind of skip its parent because we've already like gone through there. We only want to go through the children. So that's why we have this check for like if C equals parent. Any other questions? All right, that's iterative DFS. It'll be pretty useful for today's problem set and for I guess like later topics. So next, we'll be going on to a topic called tree rerooting.
So we're going to talk about a technique that you can use in programming, which is tree rerooting. And to start off, we're going to give a little problem to give a little bit of a motivation as to why we would ever use this technique. So let's say you're given a tree consisting of n nodes, and your task is to determine for each node the sum of distances from this node to all the other nodes. And so let's consider this example, and we can think about this naively. So we have this naive solution where we have this tree, and we can use DFS to sum distances to all the nodes. And at the specific tree, we have our node 1 as our root. And we can kind of look through this and we can sum all the distances intuitively. So if we go from root to 3, that's a distance of 1. And if we go from root to 5, that's a distance of 2. If we go from 1 to 4, that's a distance of 2. And if we go from 1 to 2, that's a distance of 1. So we add those all together and the sum of all distances is equal to 6. But this is not how we code this, and we have a little bit different of an approach. So for the solution, we first set node 1 as our root. So we're finding the sum of all distances to all the nodes. So our first step is to run DFS starting on that root. And for every single child of the root, we find the distance of the child, which is the distance being the sum of all distances to each of its descendants. So for example, if we're considering node 2, we're finding the distances to node 4 and node 5. And if we're considering node 3, there's no children, so the distances is 0. And then we also add the size of child, which is accounting for the edge between the child and the root. So we're accounting for this edge between 1 and 2, and we're also accounting for the edge between 1 and 3. And then we will return the sum of all distances. So this may sound a little bit confusing, but we'll walk through this step by step and break down the process. So for the naive solution, let's first consider node 2. Its descendants are node 4 and 5. Right? And so the first path is where we're finding the path from 2 to 4, and that distance is 1. And then we consider the path from 2 to 5, and that distance is also 1. So we add those two together, and the sum of all distances to its descendants is 1 plus 1, which is 2. And now let's consider node 3. This is the other child of the root. And since there are no children to node 3, the sum of all distances is 0. And so now we found all the sum of the distances for both from the children. So we can add those two together, which is 2 plus 0, and that's 2. However, we still need to account for the paths between the root and its children. And so kind of how we do this is for each node in the subtree, we add 1. So for this subtree containing these 3, we add 1 to account for that path between the root and the node. So there's 1 added for 2, and then 1 added for node 4, and 1 added for node 5. And that results is the same as the size of the subtree, which is 3. And if you add that to our answer from earlier, we get 5. And so now let's consider the subtree of 3. That size is 1, so we also add that to the distance for 1. And that means that we have our final result, which is the sum of all distances for node 1, which is 6. And that's the exact same answer as we pre-computed before. But now we have to repeat this process for all of the nodes. And the problem with this, as you can probably tell, is that the time complexity means that this code is going to time out. So we first use DFS to compute the sum of distances for one node. And then we're repeating this process for all the remaining nodes. And this results in a time complexity of O to n squared. And for trees with large n, this code takes too long to run and will exceed the time limit. So we have a different solution, which includes rerouting, which will simplify this process and also allow us to do the code and not have it exceed the time limit.
Yeah, so I guess first of all, this rerouting solution will depend very heavily on the brute force solution we previously talked about. So are there any questions on anything in like this solution? Especially like how we calculate distances? We're good? Okay. So basically I'll draw this tree out first. So we have this tree, which is 1, 2, 3, 4, 5. And using our previous DFS, we can kind of compute like the distances for all of them. And I guess for simplicity right now, to just demonstrate how rerouting works, we'll only be calculating like showing how to update subtree sizes. So I'll write the subtree sizes next to each of these nodes in parentheses. So this 5 is 1, this 4 is 1, this 2 is 3, this 3 is 1, this one has subtree size of 5. So we can calculate this like using the DFS we did in live coding. But let's say we also wanted to know like all the subtree sizes if the tree were rooted at node 3. So one way we could do that is to just root our tree at node 3. And just run DFS again to recalculate all of our subtree sizes. But that'll take like another O of n time. So is there a way we can like kind of use our current subtree sizes that we already computed to efficiently update all of our subtree sizes to reflect this newly rooted tree at node 3? So one thing to consider is that node 3 and 1 are adjacent. This only works if the two nodes are adjacent. And nodes 2, 4, and 5 are the exact same like structure here. So they have the same they all have the same subtree sizes because their structure didn't change at all. Whereas the only two nodes that actually had their structure change are the two nodes that we like swapped. So like the only two nodes that change are the old root and the new root. So what changed from one from here to here? The only change basically was we removed 3 as a child and we made it its parent. So in terms of subtree sizes, the only thing that changed for node 1 is that node 1 lost 3 as child. Additionally, if we take node 3, we see that it also gained node 1 as a child. So these are the only two changes that actually occurred in our rerooted tree, since the structure of everything else that we didn't like interact with in our rerooting stays the same. So instead of recomputing all of our subtree sums, why don't we just recompute them for nodes 1 and 3? So we can just kind of think about this intuitively. Like when node 1 loses node 3 as a child, how can we like update node 1's subtree size? How can we like what can we subtract from node 1's subtree size to kind of update like reflect this change? Can anyone give me a like a
Tree size.
yeah, exactly. So we can just subtract the subtree size of node 3. Similarly, to update that node 3 now gained node 1 as a child, we can do something very similar where we just add in the subtree size of node 1. So if we do this, notice that we'll first subtract 1 from node 1 subtree size, so this becomes a 4. Then we'll add 4 to node 1 subtree size, or node 3 subtree size, making this 5. And this is the correct subtree size since we're just like performing these two operations in series. And it only took two computation, like a subtraction and an addition to completely update our subtree sizes when we reroute, instead of taking a full O of n. So this is really useful in the case like the problem we have here, when we want to calculate like something for every node. So instead of just doing size, why don't we also try calculating the same about distances? So when node 1 loses node 3 as a child, so um so how can we update node 1's like distances to reflect that it lost 3 as a child? This is a slightly more complicated expression than that, but does anyone have like an idea for what terms we can put here?
The size of 3 and the distance of 3.
Exactly. So we'll add size 3. This basically just disconnects 3 since or like this is kind of our update function where every time we either add or remove a node, we kind of use both the distance and the size to account for like the path from your root to its child. If this doesn't make much sense, we'll do live coding and hopefully it'll be clear there. But similarly, when 3 gains 1 as a child, we'll do like this 3. We'll add in like size. Since this is basically just like we're considering 1 as like a child of 3 now. So we just kind of perform this calculation. Um, so I guess first, like, do people understand why for each child of the root we want to like kind of like this is our update function where we add the size and the distance of a child, like that's the contribution of a child to its parent.
Could you explain it?
Yeah, so let's consider our original tree. Um, let's say we want to calculate distance of 1. And um we know that distance of 2 is 2 since the distance to its children is 2, and this one is 0. So how can we calculate the distance of everything to 1? Well, the distance of this subtree relative to node 2 is 2. But relative to node 1, there's an extra edge in between there. So for every node in this subtree, the distance to node 1 is like 1 more than the distance to node 2. So we can calculate the contribution of like this subtree to the sum of distances to node 1 as just distance of 2 plus the size of 2. Since this distance is just all the distances relative to this node, and the size adds this edge for every single node in that side of the subtree. Does that make a little bit of sense? Yeah. Okay, so this kind of update function is why when we like remove a tree or remove a child and we add a child, we also perform the same kind of update because every time we remove a child and we add a child, it's just like considering one of these. So we'll now go through kind of like a live coding exercise to see how we can actually like use DFS to compute. Oh yes.
When you update this new tree, why don't you have to update the size of one?
Oh yes, you also do like you insert in like size update here and like size update. You also do have to update the sizes first. So yeah, sorry about omitting that, but yeah. Yeah.
So good question. Therefore, like the distance 2 plus size 2, right? So distance 2 is the distance of that subtree with the 2, 4, 5.
Yeah.
And size 2 is what, 2?
It's 3. It's the size of the subtree. Yeah.
Right. This 1 was the 2, 4. Okay, got it.
Yeah. So this term is just like accounting for this edge for every single node in the subtree.
Okay, got it.
Okay, so this problem here is basically the problem we were just explaining, which is you're given a tree and you want to determine the sum of the distances from some node to all other nodes, and you want to do this for every single node. So you have to like print the answer for all n nodes. So let's try and solve this using code. So our input this time is just given to us like the number of nodes and then all of our edges. So we'll quickly code up kind of our adjacency list. This is the number of nodes, and then our adjacency list will initialize to be empty. Then let's say our 2 nodes here are U and V. Then they're one indexed, so let's make them zero indexed. And then we'll add them to our adjacency list. So now we've constructed our adjacency list similar to last problem, and we can kind of copy and paste our DFS since we also need to compute subtree sizes here along with the extra distances array. So we'll also make like distance 0 times n. We'll call this like DFS initial. And so we similarly process like queue our children in, but the only difference is now when we update our size array, we should also update our distance array. So we can use our same kind of formula here, where we have that we add the contribution of this child, which is just the size of the child plus the distance of the child. So what this does is it solves our problem for every single for this specific root. So for example, if we root our tree at 1, or if we call DFS initial 0, it will solve this problem for node 0, and our answer for node 0 will just be at distances 0. So the naive way to do this would just be to iterate through every node, like for I in range, and we'll call like DFS initial on that node, and then we will print out, since I is the root, the sum of the distances from it to all of its descendants is just the sum of the distances from it to everything in the tree. So we'll just print out distance of I here. We should also reset this every time. So if we try to do this, we can see what we, oh, no. We also need to reset the sizes. So if we try doing this, we get 69588, which is the correct answer. So like our 9 DFS does work correctly. However, since we're computing an O of n DFS for every single node, this will take way too long, especially with n is at most 2 times 10 to the 5. So instead, we can use our tree rerouting approach. So I'll like delete all of this. We'll just do an initial DFS at node 0. Yes. And what this does is it just kind of populates our disk with this as the root. Then we'll define kind of a reroute function where we have the original root and we have a new root. And we kind of want to like rotate the tree from like here to here. And so how we do that, remember when we change from the original root to the new root, our original root loses the new root as a child. So what we do is we can, interesting, we can update the sizes. So like size of the original, we subtract the size of the new, and the size of the new, we add the size of the original since it gained, oh wait, I should say new gains original as child. And the order of this is important because we first want to have the original lose the new root, and then we want to connect it, since that's kind of like the order we could visualize that. So in addition to updating our sizes, we also need to update our distances. So when the original loses the new, we can subtract like size new plus distance new, since that's how we that's like our update function. And then we can also update the distance of our new root with so after we run this with original as our old root, new being adjacent to our old root, new will become our adjacent root, and all of our size and dist arrays will reflect this new kind of tree structure. I'll add an extra case at the beginning just for simplicity later on, because sometimes we'll have a none in there and we want to do nothing. So then we can now do our like DFS reroute, which will basically kind of reroute to every single node in our tree so we can compute the answer for every node in our tree. So we'll start again with our stack kind of thing from earlier with root none. Actually, I'll copy this over. So since we already have a kind of DFS template, we'll just go ahead and put this here. So there's several changes we need to make. First of all, we don't need to kind of do any of this stuff. But when we begin processing a node, we want to make sure it is the root. So what we can do is we can reroute from the parent to the current node. So this will set node to be the current root. And we can make our answer array. We can set answer of node is to be dist of node, since node is now the root, and the answer, like the sum of distances to all its descendants is the sum of the distances to the entire tree. So we can calculate the answer here, but now when we finish, we also want to kind of reset everything to the way it was earlier. So we can just reroute back from the node to the parent. So this will kind of reset things for the parent so that they can also bring it back to their parent and so on. So basically, when we start processing a node, we want to bring the node to it, the parents to it. And when we're done processing a node, we want to like return the root back to where it came from. So if we do all this processing, like every node will have a turn to become the root. And so we can kind of calculate the answer for every single node. So if we run DFS reroute of 0, then what should happen is that our answer should populate kind of with the answer for all of our nodes. So we can just print our answer and see what it prints. So this is the exact same answer we got by doing things naively, except now we're using a rerouting technique that speeds up our like thing from not having to do an n squared DFS each time, but just doing simply kind of like 4 addition subtraction operations every time. So 69588, 69588, we'll try and submit this now and see, make sure it works. Yeah, so this ran in 700 milliseconds, so it's like, since this requires 2 DFSs, like it'll take more time, but it's still pretty comfortably within the time limit. Are there any questions on either like this reroute function or how we like do DFS to set everything as the roots?
Wait, so the time complexity for the rerouting one is
O of n.
O of n.
Since your initial calculation takes O of n, and then when you reroute, you're just kind of running a new DFS that takes O of 1 to kind of reroute to each neighboring element. So this rerouting is also O of n. So the total time complexity is O of n as well.
It's like n plus n.
Yeah. Okay, any other questions? Yeah.
It's always faster than the recursive version too.
Iterative. I think in Python, basically the answer is yes. Yeah. Okay, any other questions? Okay, we're kind of low on time, but we'll go on to our next topic, which is centroid decomposition.
So centroid decomposition is also another technique that you can use to simplify some time complexities. We're going to start with definition of a centroid. The centroid of a tree is a node that when you remove it from the tree, it results in a forest, which is basically multiple subtrees that are equal to or smaller than half the size of the original tree. So for example, if we have a tree of size 10, if we remove the centroid from this tree, all the remaining subtrees would have a size equal to or less than 5. So let's look at this concept further with an example. So here's an example of a tree of size 5, right? In order to find the centroid of this tree, we can start with an arbitrary node V to test our centroid conditions. So if you recall, a node can only be a centroid if the subtrees are equal to or less than half the size of the full tree. And we use floor division in order to find this condition. So 5 divided by 2 with floor division is 2. So in this case, the subtrees of a centroid would have to be size 2 or less. So let's say our arbitrary node is 1. So we have our node 1 is the node that we are considering. If we remove node 1, we would have two subtrees. We would have one of size 1 and one of size 3. However, node 1 cannot be our centroid because the centroid of size 3 exceeds our condition. So our condition is violated. So it can't be the centroid. So now we have to try this again, but with a different node. But the node needs to follow two conditions. So the next node needs to be adjacent to the previously tested node, but the next node also must be within the subtree that is greater than n half. So if we look back at this subtree, this is the one that exceeds the violation. So we have to find a next node that was adjacent to the previous node and was in this subtree. So our next node has to be node 3. So if we remove node 3 from this, we have two subtrees. Actually, we have three subtrees, one of size 2 and one of size 1. And this means that node 3 is the centroid of our tree because it fulfills the condition. All the subtrees are equal to or less than 2. So now let's consider this, but with an even tree. So if we have a tree with an even size, like 4, we can look and see where the centroid is in this scenario. So there are actually two centroids of this tree. If we remove node 1, this results in subtrees of size 1 and 2, both of which are smaller than or equal to 2. But if we also look at node 3, removing it also results in a subtree of size 1 and a subtree of size 2, which also fulfills our condition. So the overall conclusion is that odd trees only have one unique centroid, and even trees can have either 1 or 2. They don't always have to be 2, but in certain cases, it can be 2. And if there are two centroids, they are adjacent to each other. So the overall idea is we first select an arbitrary node V to consider, and then we perform DFS on node V, and we set up the subtree sizes. And starting from node V, we check whether or not the conditions for the centroid is met at V. If we do meet the conditions, we return that node as the centroid. But if we don't pass the conditions, we move to an adjacent node that is within the greatest subtree size, and then we go back to step 3 and then repeat the process. However, we cannot revisit any nodes, so we have to create a visited nodes list, and that's like some nuance that you have to consider. So the overall time complexity of this is first we select an arbitrary node, so that's O of 1. And then we also do DFS, which is O of n. And then once we start at V, that's O of 1, find centroid O of n. So the final time complexity is O of n, where n is the number of nodes. I don't know if we're too short on time.
Skip the next part.
Skip them. Okay,
Okay.
so we're gonna go do live frame.
So yeah, I guess first, does anyone have any questions on, I guess, the centroid finding algorithm? If it doesn't fully make sense, I'll also explain it as I code this. So okay, so this problem is literally called finding a centroid, and the problem is to find a centroid of a tree. Yeah, so I will open this up. I'll copy over. The input is the same as last. Okay. The input is the same as last time. We just don't need the rerouting stuff. But we also do need to calculate subtree sizes for centroid, because we need to figure out, like, how big are subtrees to determine if it is a centroid. So what we can do is we'll create our like def centroid, and we'll start at some like root. So we'll call like the node we're currently at V. So like while we're just complete this, keep going through this loop until we find a centroid. So how do we tell if a node is a centroid? So I'll claim that if any of its children, if all of its children have size less than n over 2 or less than or equal to n over 2, then it will be a centroid. And you might be thinking, like, well, what about the parent? Like, if we remove that subtree, like its parent forms another subtree as well, right? But there's a special property of this algorithm that will guarantee that the parent will also have be in a subtree of size at most n over 2, which I'll explain a little later. But I'll first implement this algorithm. So we want to iterate through all of its children. We'll also have the parent. And then, so this is one of the children, and we want to kind of check for the max children. So we'll say like max child. And this will be like subtree size, comma, node. So we'll set like max child to be the max of itself and this new child. So the subtree size of this new child is size of C. And the second element of the tuple is the actual child. So what this does is it will find kind of the max child and the index of the max child. So after we do this, we can check. So if like max child, if the size of the max child is at most n floor division 2, that means we found a centroid. We'll just return V as our centroid. Otherwise, what we need to do is we set V to, we set first the parent of this new child is V, and we set V to be the index of our max child. So now I guess like, why is this check sufficient? Because I guess like, for example, in this tree, when we split, if we're testing this as our centroid, we're only checking like kind of the children. But what about this subtree up here, right? That like we also need to make sure this like I guess it's not a subtree, but these two nodes also have less than n over 2 in them. So the reason this works is because every time we do like kind of go down, this means that the subtree that we go down into has size at least n over 2, which means that everything not in that subtree has size at most n over 2, meaning that, for example, if we go down here, this means that this subtree has size at least n over 2, which means that everything not in the subtree has that size at most n over 2, meaning when we look at this one and we see the children are less than n over 2 or less than or equal to n over 2, everything else also must be less than or equal to n over 2. So it still satisfies the properties of a centroid. So if we take this algorithm and we just like we can just print the centroid starting at root 0, since that's the node we picked to DFS from. Let's try this. We need to 1 index it because of CSES. So we print the centroid, that's 3. We see they also have 3. And let's try and submit this code. Okay, so it ran pretty fast, 520 milliseconds. Are there any questions about this centroid code, either like from a correctness standpoint or like what a specific line does? Anything? Yeah.
Explain why the and like n over 2 check works. Yes.
Like why we know that it's like
Yeah.
parent. So when we go from a parent to one of its children, since that's kind of what our algorithm does, it goes like it keeps going down. We know that the subtree size of this child or this must be at least n over 2. Because if it wasn't, then like our max child would be less than n over 2 and we would have already terminated. So we know this must be at least n over 2. So everything else must be at least n over 2, since the total number of nodes is n. So that means that at every point we know that it's like everything not in the subtree must have size at most n over 2. Exactly. So that's kind of why we don't have to really worry about the parent, since it's kind of a property that's maintained as we go through our algorithm. Any other questions? Alright, so we're kind of out of time here. We have an application of this as well, but you're welcome to read through the slides about it. But here's our attendance form. We also have a raffle counting form for you all to self-report how many raffle tickets you have. We will be we'll be verifying the number of raffle tickets for the winners. So try your best to make your count accurate. Yeah,
It's one for attendance and then you get more for other things.
one per attendance, one per problem solved on video.
By today.
So far. Yes, there's more details on the form for specific. But thank you all for coming today. We'll have problem solving session and we'll have Subway today for dinner. Yay. Okay.